When I was 11 years old, our apartment was burned down due to electric fire. We waited downstairs watching the black smoke coming out of the living room windows. There's nothing you can do in those situations other than waiting for the firefighter to come. In the next 3 months, me and my family living in the basements of our apartments. A safety incident like this can be quite costly to a family. And when we talk about current battery technologies, safety is especially important. We look around ourselves, we're literally surrounded by batteries. We have batteries in our phone, computers, cars. However, there's been quite a bit of high-profile safety incidents related to battery. When I talk about Samsung phone, you may still remember that years ago, those Samsung phones would like to be light on fire. There is also instance related to Tesla cars or battery manufacturing facility that would like to be light on fire. The reasons why battery is so flammable these days is because of the flammable organic solvent molecules in the battery. Those molecules are organic, volatile, and would like to be easily caught on fire. So to resolve that issue, quite a bit of work has gone around into developing an alternative, safer electrolytes. I'll separate them into 3 categories. The first one is the solid-state ceramic electrolytes. It's complete rock-hard solid, quite different from existing liquid-state electrolytes. However, to use them or to manufacture into a battery, it really requires a revamping of the entire battery production facility, which can be quite costly. Into the more manufacturable electrolytes, we have polymer-based electrolytes. Polymer electrolytes lacks ion conductivities, and gel electrolyte is still flammable. I'll go deeper into these 2 types of electrolytes. Polymer electrolytes replacing the flammable solvent molecules in the normal electrolytes with polymer. Normal electrolyte has small molecules, they move quite fast, polymer move quite slow, and as a result of that, the ion conductivity of the polymer electrolyte is quite slow. And that makes those electrolytes have to be run at elevated temperature, like 60 to 80 Celsius. So to solve the conductivity issues of polymer electrolytes, we use gel electrolytes. We added more solvent molecules into those electrolytes. With the conductivity issue solved, gel electrolyte is still flammable, which makes them hurt the safety issue with the existing solvent molecule. The conundrum is really on the solvent molecules. One side, we need the solvent molecules to improve the conductivity. On the other side, we don't want the solvent molecules because they cause safety issue. The important question here is that can we strike a balance in the middle where we balance between ion conductivity and safety for solvent molecules? Or a more important question to ask, can we make a non-flammable electrolyte with solvent molecules? Here we show that we can. So in this video, we soaked a glass wall with our electrolytes and commercially available electrolyte that is in our phone and our tablets. We soak it in a glass wall, so the glass wall itself won't burn. For our electrolyte, we can see that when they approach with the flame, it's only charring that happens. But for commercially available electrolytes, the flame was sustained until all the solvent molecules are exhausted in the system. So what is the secret? The secret is that those solvent molecules are actually anchored by salt and polymer in the system. Here I show the structures of our electrolytes. It has a siloxane polymer backbone. Those polymer backbone are silicone, makes them quite thermally stable. We added a PYFSI units. So those are like room temperature molten salt. They can solvate lithium salt. We added lithium FSI salt in the system. They're the main carrier of lithium ion in the lithium ion batteries. And then we added DME solvent molecules. In this system, the electron-rich DME, oxygen in the DME molecules, like to coordinate and interact with the positively charged nitrogen and lithium group. And those interactions or those coordinations effectively anchor those solvent molecules in the system, makes them no longer volatile. And those interactions or anchoring interactions were able to confirm with DFT and Raman spectroscopy. We call this special type of electrolyte safe, solvent-anchored, non-flammable electrolytes. We're wondering, what anchoring is this actually happen so it can render the electrolytes non-flammable? For that, we turn into the measurements of relative saturations. Relative saturations is a measurements like humidity in the air. When you walk into a greenhouse, the humidity is 100%, which makes you feel the greenhouse is really humid. The same concept can be applied to solvent molecule as well. In a closed container, if the relative saturations of solvent molecule is quite high, that means that the solvent molecule is quite volatile, making the electrolytes flammable. We can measure the relative saturations of solvent molecules in different electrolytes. For the commercially available electrolytes, the relative saturation is quite high, which makes that electrolyte flammable. We add more salt into the system, we lower the relative saturations, but it's still quite high and flammable. Adding more polymer into the system, we continue to lower the relative saturations. However, the electrolyte is still flammable. In our unique formulations of SAFE, we have 63 weight% salt and some polymer in the system. Our electrolyte SAFE only has 2% relative saturations, and it's no longer flammable. Other than the flammability issues, our SAFE electrolytes is also quite conductive. Previously, we talked about the conundrum between conductivity and safety for the batteries. On one side, we need the solvent molecules for conductivity. On the other side, we don't want them for safety. In our unique electrolyte compositions, we can anchor the solvents in the system and strike a balance between the conductivity and safety of the electrolytes. Our SAFE electrolyte has elevated conductivities compared to other existing polymer-based electrolytes at a wide temperature range. Other than conductivities, SAFE electrolyte is actually a liquid state, which is different from other ceramic solid-state electrolytes. It can be readily used with existing battery electrodes and battery stack geometries without additional modifications, which makes them quite manufacturable. SAFE electrolytes can also be readily integrated into batteries and show stable long-term cycling performance. So they're just as a replacement for commercially available electrolytes, but it's just being safer. Here it shows that battery with SAFE electrolyte can stably cycle, charge and discharge for more than 11 months, and we're not observing any reductions of the battery capacity shown over here. So as a summary, we show that SAFE is electrolytes that fulfill the requirements of manufacturability, conductivity, and non-flammable. SAFE is a liquid, and by anchoring the solvents in the system, we can strike a balance between conductivity and safety. Going forward, we're really excited to bring the SAFE technology to the commercial markets, and there's a lot of ongoing work in terms of developing SAFE technologies, making the technology more economically accessible and further improve the performance of the SAFE technologies.